Welcome back to the Deep Dive. Today, we are diving into something genuinely extraordinary. We're talking about cosmic visitors, objects from completely different star systems, interstellar objects, ISOs for short.
That's right. And until fairly recently, we really only had two confirmed ones to talk about. There was One-Eye Oumuamua.
Ah, yes, the really weird sort of cigar-shaped one that acted a bit like a solar sail.
Exactly that one. And then there was Two-Eye Borisov, which, well, it looked and acted pretty much exactly like you'd expect a natural comet to, just one from very far away.
And those two, as different as they were, they gave us our first real, physical samples of material from outside our own solar neighborhood, didn't they?
Invaluable stuff.
Yeah.
Direct evidence, really, helping us piece together how planets might be forming elsewhere in the galaxy. It's a huge deal.
Absolutely. But now there's a third visitor on the scene. Meet 3I Atlas. It popped up in detections back in July 2025, found by the ATLS facility down in Chile.
Mm-hmm.
So we've gathered all the key source material on this one. And our mission today is basically to unpack it all. We want to tackle that big question head on. Is 3I Atlas, just another natural interstellar comet?
Mm-hmm.
Or is there something more unusual going on, maybe even, dare I say, artificial?
Well, one thing we know for sure right off the bat is that it is interstellar, no question there. Its speed is just phenomenal, clocked at around 137,000 miles per hour.
Wow.
And its orbit is what we call hyperbolic. That means its eccentricity value is greater than 1. That confirms it's not gravitationally bound to our sun. It's definitely just passing through.
Okay, so definitely a traveler. Let's dig into this new interloper then. Maybe start with the case for it being natural. What did the initial observations show?
Right. So the ATLA survey, that stands for Asteroid Terrestrial Impact Last Alert System, they first spotted it July 1st, 2025. Confirmation came pretty quickly after that, checking its position, brightness.
Barometry and photometry.
Exactly. And they even found some pre-discovery images going back to mid-June, which helped nail down the path.
And what about that path? Its trajectory?
So it's coming in at a pretty steep angle compared to the plane where most of our planets orbit. Its closest point to the sun, perihelion, that was expected around late October 2025, about 1.4 astronomical units out.
So further out than Earth.
Yeah, a bit. And its closest pass to Earth was even further, around 1.8 AU. So importantly, never any threat to us.
Okay, good to know. Now, the big argument for it being natural, you mentioned comets.
Yes, the activity. Unlike Oumuamua, which was just this mysterious point of light, 3I Adia showed definite cometary signs almost immediately.
Like what?
A visible coma, that fuzzy envelope around the nucleus, and even a developing tail. Actually, it was apparently much more pronounced, much more active looking than either of the previous ISOs we'd seen.
Interesting. So it looked, initially at least, like a classic interstellar snowball, basically.
Pretty much, yeah. The early thinking was, okay, this is probably an icy body, maybe kicked out of some distant planetary system long ago.
And did the composition back that up? What did spectroscopy tell us?
Well, early spectroscopy seemed to fit. It showed gases like colloidal water, CO, carbonyl sulfide, things we see in our own comets, and evidence of water ice, too.
So familiar stuff.
Familiar stuff. It suggests it formed in a giant molecular cloud, similar to how our own comets likely formed. It all seemed pretty consistent with, known cosmic processes we see across the Milky Way.
Okay, so if it looked so much like a regular comet, why the huge international effort to observe it? I mean, you mentioned coordination.
Well, just because it looked typical didn't mean we shouldn't study it intensely. This was an unprecedented opportunity.
Right.
So they threw everything at it. A whole battery of ground-based telescopes, SOR, the Zwicky Transient Facility, and others. Coordinated that with NASA space assets, TESS, SWIFT, SphereX.
Even Perseverance on Mars got involved.
Yep. Getting a view from a different planet gives you a different angle, different perspective. It all helps build a complete picture. And this whole observation campaign is planned to run until maybe March 2026, trying to squeeze out every last photon of data before it gets too far away.
Okay, so a massive effort to confirm it's a natural comet. But despite all that, the data started to, get a bit weird, didn't it?
Yes. This is where the simple natural comet explanation starts to run into some problems, some pretty big ones, actually.
Here's where it gets really interesting then. Let's pivot to these strange characteristics, the ones that are harder to explain away.
Okay, first up is what some sources are calling a profound size paradox. It comes down to how big this thing seems to be.
How big are we talking?
Initial estimates, based on its brightness and assuming typical comet reflectivity, suggested a nucleus maybe up to 20 kilometers in diameter.
20 kilometers. That sounds substantial. Why is that a paradox?
Because our models of how many objects should be floating around interstellar space just don't predict finding something that big so soon. Meaning, based on how much material we think gets ejected from star systems, we should have detected literally about 1 million smaller, maybe dust grain to meter-sized objects before stumbling upon a 20-kilometer giant.
Wow, okay. So finding something this massive implies either there's vastly more interstellar material out there than we thought,
Like 10,000 times more, potentially?
or maybe it's not a typical comet and its nucleus is actually much smaller, perhaps less than, say, 0.6 kilometers across.
Exactly. Finding something that big really throws a wrench in our understanding of how stuff gets kicked out of solar systems and populates the galaxy. It just doesn't fit the expected distribution.
Okay, size is one puzzle, but you mentioned the chemistry earlier seemed normal, but then maybe not.
Right, that's the second big anomaly. Later, more detailed spectroscopic analysis turned up something really strange. Significant emissions of nickel.
Nickel. Okay, what's weird about nickel? Comets have metals, right?
They do, but usually if you see nickel, you see iron alongside it in predictable ratios.
Yeah.
With 3 idealists, they found nickel, but without the corresponding iron signatures.
And that's unusual.
It's never been observed before, not in any comet in our solar system. We don't currently have a known natural process that readily explains nickel enrichment without accompanying iron in a cometary context.
Huh. Okay, that is weird. And wasn't there something else about the gases, or lack thereof?
Yes, get this. Despite having that visible coma, that fuzzy look, and showing some weak dust activity, really sensitive analysis found no spectral signatures of the expected cometary gas emissions.
Wait, so it looked fuzzy like a comet, but wasn't actually spewing the right gases?
Precisely. It's losing some mass, creating that haze, but it's not releasing the volatile gases like water vapor or CO in the way we'd expect from a sublimating icy nucleus. It's fundamentally different in its behavior compared to 2I-Borsov, which was, a textbook case.
Okay, so the composition is weird, the size is paradoxical.
Yeah.
What about its movement, its dynamics?
Ah, yes. This is where the speculation about other origins really heats up. For one thing, like Oumuamua, 3I Tailus showed non-gravitational acceleration.
Meaning, it wasn't just moving under the influence of the sun's gravity. Something else was pushing it slightly.
Correct. But unlike a normal comet where outgassing can provide that push, here we have that lack of gas emission we just talked about. So what's causing the acceleration? It's another puzzle.
And there were orbital alignments too, weren't there? Something about the ecliptic plane.
Yes, the geometry is eyebrow-raising, let's say. Its orbit is retrograde, meaning it goes around the sun the opposite way to the planets, but its orbital plane lies remarkably close within about 5 degrees to Earth's orbital plane, the ecliptic.
And that's unlikely.
Highly unlikely for a random visitor from interstellar space. If you just model random trajectories, the probability of an ISO ending up in an orbit tilted so closely to our system's main plane is only about 0.2%. Very low odds.
Okay, 0.2% is low, but maybe just a coincidence.
Perhaps. But then there's the timing. This is where it gets really interesting, as you said. It didn't just fly by. Its arrival seemed almost choreographed.
Choreographed how?
It made remarkably close approaches to several planets in sequence. Venus, then Mars, then Jupiter. We're talking approaches of 0.65 AU to Venus, 0.19 AU to Mars, 0.36 AU to Jupiter.
Okay. And the odds of that sequence happening by chance?
Vanishingly small. When you calculate the cumulative probability of a random interstellar object having that specific timing to make those close passes to those specific planets in that order, the odds are about 0.005%.
0.005%. That's basically statistically impossible for a random event.
It's incredibly improbable, yes. This confluence of anomalies, the size, the nickel, the lack of expected gases, the non-gravitational push, the orbital alignment, and the synchronized planetary flybys, it's what has led some researchers to seriously consider non-natural possibilities.
And this brings us to people like Avi Loeb at Harvard, right? Proposing it might be artificial.
Exactly. Loeb and others have pointed out that this specific trajectory, particularly reaching perihelion on the far side of the sun from Earth, is actually optimal if you wanted to perform a specific maneuver.
A maneuver, like braking.
Precisely. A reverse solar O-berth maneuver. It's a highly efficient way for a spacecraft to use a star's gravity to decelerate and change course significantly.
And doing it behind the sun would keep it hidden from us.
During that critical phase, yes. It allows for braking without easy detection from Earth-based telescopes. So the argument goes the trajectory looks suspiciously well-suited for an artifact wanting to slow down and perhaps observe our system, while staying somewhat concealed initially.
And this fits into that broader idea of SETA, the search for extraterrestrial artifacts.
It does. The thinking there is that maybe sending physical probes, perhaps self-replicating ones, across the galaxy over vast timescales is actually a more efficient or likely method of exploration for an advanced civilization than, say, constantly beaming out powerful radio signals.
So instead of listening for messages, we should be looking for stuff, objects.
Potentially, yes.
Yeah.
Actively searching for physical evidence that might already be here, or passing through, maybe even parked somewhere nearby, observing.
It's impossible not to think back to Oumuamua here, the first one. It also had that non-gravitational acceleration without a clear cause, right? No coma.
Exactly. And Oumuamua had that very strange light curve, suggesting it was extremely elongated, or more likely, very flat and thin, maybe like a disk. That's what led to the speculation it could be a deliberately thin craft, like a light sail, being pushed by sunlight pressure.
So with potentially multiple weird objects showing up, it makes sense people started thinking we need a way to categorize these things systematically.
Absolutely. That led to the development of the Interstellar Object Significance Scale, or IOS. Some just call it the Loeb scale.
What's the purpose of that scale?
It's basically a framework, a quantitative scale from 0 to 10, designed specifically to help scientists evaluate these ISOs and any potential technosignatures, signs of technology in a rigorous way.
Sort of acknowledging that finding these things might become more common.
Precisely. We're entering an era, especially with new telescopes coming online, where we expect to find more ISOs, maybe regularly. We need a system to classify them based on how anomalous they appear.
Okay, so applying that scale,
Mm-hmm.
where do our known visitors fall? Borisov, the comet.
2I Borisov is a clear level 0, completely consistent with known natural phenomena, textbook interstellar comet.
And Oumuamua and this new one, 3I-ATLS.
Both of them, because their multiple, persistent, unexplained anomalies, are currently classified as level 4.
Level 4, what does that signify? Is that high?
Level 4 is defined as an anomaly meeting potential technosignature criteria. It basically means the object is weird enough in multiple ways that we can't easily explain naturally that the possibility of technology has to be considered. It's the threshold that triggers more intense observation and investigation, specifically looking into all possibilities, including the artificial one.
Now, it's crucial here to bring in a balancing perspective, right?
Mm-hmm.
What does the official government side say, like the Pentagon's ARO office that looks into UAPs?
Yes, that's important context. The All-Domain Anomaly Resolution Office, AARO, has stated that while they do study very anomalous objects, which includes UAP-UFO phenomena, they have so far found, and I quote, no verifiable evidence of extraterrestrial beings, activity, or technology.
So no confirmed alien tech from their end, despite looking at weird stuff.
That's the official stance, yes, which highlights the situation scientists are in with 3I Atlas. You have to hold two conflicting ideas at once.
Either it's natural, formed by processes we just don't grasp yet.
Or it's something else, something manufactured. That weird nickel signature without iron, combined with that incredibly improbable trajectory and timing, it makes 3I Atlas an absolutely vital case study, no matter what the final answer turns out to be.
And finding that answer feels pretty urgent now, doesn't it? With more potentially on the way.
Absolutely. Facilities like the upcoming Vera Rubin Observatory are expected to ramp up ISO detection rates dramatically. We might be finding new ones every few months soon.
So that Loeb scale is going to get a workout.
It will be essential for deciding which objects need immediate, focused follow-up, which ones warrant spending precious telescope time on.
And aren't there already plans to, go visit the next weird one?
There are. The Galileo project, which is privately funded, is actively working on designing a mission concept. The idea is to have a small, fast spacecraft ready to launch on short notice to intercept the next Oumuamua-like object that comes through.
To get actual close-up pictures.
High-resolution images, yes. To try and see what these things actually look like up close before they vanish back into interstellar space. It's a huge shift in thinking.
It really is. Moving from passive observation to potential active interception. Okay, so let's leave our listeners with a final thought to chew on.
Go for it.
Based on the current scientific estimates, the Milky Way galaxy is just teeming with these interstellar objects. Trillions upon trillions, maybe more.
The numbers are staggering. Every star likely ejects something like an Earth mass worth of material over its lifetime. Add it all up, and you get maybe 10 to the power of 24, up to 10 to the power of 26 of these things wandering the galaxy.
So here's the thought. Given that almost incomprehensible number, that vast galactic population of debris? What if even a tiny, tiny fraction, like an infinitesimal percentage of all that stuff, isn't natural rock and ice? What if some of it is artificial? Maybe just discarded probes, old defunct technology, cosmic flotsam from civilizations long gone? Think about the statistical implications of that.